Geometry and sorry. Okay,
Yeah,
okay.
it's a recording in progress.
Yeah, okay. I'll just repeat that line again. The last talk today will be from Professor Venkata Balaji from IIT Madras. His interests are in algebra, geometry, and algebraic and complex geometry. And he'll be talking about curvature from the viewpoints of perception, physics, geometry, analysis, topology, and calculus. Over to him.
Yeah, okay. So, well, I can see some chairs are empty. I don't think I can see everybody. If some, so, so let me wave my hand, and you can also wave your hands. Okay, and yeah, great. Okay, so if anybody has any questions to ask, please don't hesitate to stop, and maybe so somebody has to come close to this and talk. Or probably Krutarth can ask, he can hear the question and then he can ask me. So don't hesitate to talk back. It need not, my lecture need not be a monologue. It can very well be a discussion. But of course, don't you know interrupt me too much, so that I will not be able to do much. On the other hand, if there's something that's pressing your mind, then you should speak it out, and I'll be very glad to explain. So, okay, so I think everybody is having a fun time enjoying mathematics. Okay, so normally mathematicians are very serious people. Okay, and they are a secluded lot, and that's because that they are very meticulous. Okay, and they want proofs for everything. They won't believe unless there is a proof. Nobody believes. Okay. On the other hand, mathematics is a fun thing if you learn to enjoy it. And it has, of course, it has applications. Mathematics is everywhere. That's the, that's my, let's say, mantra. And now it is increasingly clear that, if you go to anything, whether it is humanities or, sciences, or you go to arts, mathematics is there. Okay. To explain to you, try to explain at least, this idea of curvature. So I think people are, this is a heterogeneous lot of students. I think some of you are probably from ninth standard. How many are you from ninth standard? Ninth grade? Uh, you can raise your hands. 10th grade? 10th grade, there are quite a few, okay? So you know some geometry. What about 11th grade? 11th standard? Okay, quite a few. And then 12th standard? Anybody from 12th? Nobody from 12th? Or there are some I cannot see in my, I don't know. And are there any undergraduates? No, there are no undergraduates. There are a couple. Okay, fine. Okay, it's a kind of mixed bag. So so I will say some some ideas about what curvature is all about. And you see this. So I'm going to write. So please let me know if the screen is visible and it's legible. All right. So you see. So the idea is curvature. That is the key word. Okay. And the mathematical subject that is or topic that is connected with curvature is differential geometry. Okay. And well, it has several hundred years of existence. Okay. Notably, from the time of Riemann, the person whom you might know as the inventor of the Riemann integral, okay, and also the proponent of the so-called Riemann hypothesis, which is, the most unsolved, important unsolved problem in mathematics as yet, okay. So you see, so what is this idea of curvature? So my title says curvature from the viewpoint of, perception, then physics, then geometry, then analysis, then topology, and then calculus. Okay, so the thing is that I'll try to explain each of these points of view So let us go, from the very, let us say, intuitive point of view or geometric point of view, and that is, so what you think of is, you think of a curve, all right. Uh, so I've now driven I've drawn a curve on the plane, and you can think of this as, I'm driving a car or a vehicle, cycle or motorbike on a, if you want, on a flat ground, okay, and I will trace a path, okay, and so if you want, there is a direction in which I'm going, if you want, or you can see this as a curve in the plane, okay, and you are familiar with nice curves like circles and uh, sine curves and so many things. You are familiar with such things. So the idea is that you take a point on the curve. If you call the curve as gamma, then you take a point P on this curve. And what you want to do is you want to talk about the curvature at P. So the question is, how are we going to understand what the curvature is? So what is the curvature? The curvature is the let's start with a very preliminary kind of idea. The curvature is the extent to which something curves. Okay, that's as simple as it can be. So curvature should be the extent to which the curve gamma curves at the point P. Okay, that is the curvature at P, and we will call this as, I will use kappa sub P. Okay, or if you want, I can also use kappa of P. Kappa is K. It is the K in Greek, standard symbol that's used for curvature. So it's a function of P, and you can see that at this point, the curvature is a kind of, it's less curved. Whereas if I go to, let us say, a point, suppose I turn this around like this and go to a point P dash here, or let me call it as Q if you want, then here you see, here also I will get a curvature, and here the extent to which the curve is curved here is more. It's more curved here, and it's less curved here. So you can see that the curvature at Q is going to be greater than the curvature at P. Okay. Therefore, the extent to which the curve is curved is what we are trying to measure. Okay. Now the point is view. So this is a very intuitive thing, and this is something that everybody will understand. Okay. Now I think your video is frozen. I don't know. Are you still able to hear me?
Yeah, we can hear you.
Yeah, but I can't. Your video has kind of now
Yeah,
it's
we're rejoining. Yeah. Can you see us now?
not yet. Wait. Um,
Check it. I think it should be working.
mm,
Yeah, the video is in Krutarcha's account and not Tessellate Stems.
yeah, no, I can see. So I think I have to again, yeah, now it's okay. So one of the nice things is that otherwise I will feel as if I'm talking to a wall, okay, and it's very difficult for me. And also, if you have any questions, if somebody raises a hand, I can see, and I can ask I can respond. So that's great. Okay, so you see, so this is a very simple thing. The curvature of a curve is just the extent to which the curve turns, and with this very intuitive, very simple kind of understanding, the curvature at P is certainly less than the curvature at Q. Okay, and because it's less curved at P and it's more curved at Q. All right, but you see, mathematicians are not happy with these kinds of things. This is less, that is more, and mathematicians want a. So this is what mathematics is. You want to really formulate this. You want to give it a definite meaning. Okay, and so this has got to do with definitions And once you have definitions, it's got to do with being able to write formulas and things like that. So the question is, this is very, very qualitative. Okay, how are we going to quantify this? So this is, how do you quantify it? So that is the math part. So see, this is a very general thing. Why is mathematics everywhere? Mathematics is everywhere for this reason. See, whatever you see, you want to measure it, okay, and you have some idea of measure. That, for example, a stone weighs less than a big rock, and these kinds of things. But then, that's just qualitative. But if you want to really measure it, then you have to really put numbers. Okay, you need units, and then you have to put numbers. And of course, once you go into the science of measurement, that's exactly what physics is. It's a science of measurement. And so you get these numbers. That's what measurement is. Once you get these numbers, then you need to know how they are related. Because, for example, for example, in nature, you see that, when you, for example, throw something in the air, the angle at which you're throwing it and the wind resistance, etc., that determine the trajectory of whatever you throw as a projectile. Okay, gravity also has an influence. So you see, there are now many variables. So every quantity you measure is affected by other quantities. Okay, so this way you come to this idea of dependent and independent variables. And therefore, what happens is that this is function theory. So what happens in function theory is that you're trying to measure certain quantities which depend on some other quantities. And then you try to divide these quantities as independent variables and dependent variables. And then when you say it is dependent, it's still qualitative. You want to write down a formula or equation for the dependence. And that's where the math comes in. Okay. So the point is, mathematics is everywhere, because everywhere you have to quantify, everywhere there are variables, and you need formulas. And what happens, interestingly, is why calculus comes into many of these things is because most of the phenomena that occur in nature, most of the laws of nature, don't directly relate the variables, but they relate changes of the variables, okay, which are understood as derivatives in calculus. Okay, so when you throw an object in the air, you see its velocity changes. Okay, and the velocity change is like a vector, and this velocity is what is rate of change, with time rate of change with respect to the displacement. So there is a variable there, and the variable is actually now the derivative of the displacement, which is the velocity. So most of the laws of nature, most of the phenomena in nature, they involve derivatives of variables. And that's why these laws, when you write formulas for them or discover formulas for them, they come out as differential equations. Okay, and then you have to solve the differential equations to get the formulas for the variables, because you have to remove the derivative. But to remove the derivative, you have to integrate. Okay, and integration is what you do when you solve a differential equation. So you see, that's how calculus comes in. So you see anything in nature, okay, functions will come in, independent variables will come in, derivatives will come in, differential equations will come in. You need formulas for these variables, so you have to integrate. Okay, and so calculus comes in. Okay, so all these things are intertwined. Okay, so here, so that's all about quantification. That's what mathematics is all about. Okay, so mathematician, as far as a mathematician is concerned, he's worried about, you tell me something, I'll not believe you until you give me a formula, and you give me a proof of that formula. Okay, and that's how mathematicians think. All right, so when I say here that curvature is has got to do with the extent to which a curve is curved, then I'm only being qualitative, and I'm not being quantitative. So I need to quantify it. How do I do it? So the way to do this is, I will give you at least a few. I will give you 2 or 3 approaches. The first one is, let us say, from physics. Then the second one is from geometry. And the third one is from calculus. And then there are others. I just put ... Okay, so let me go from the very simple point of view, which is physics. So one of the things that you do in mathematics is that you try to look at a simple case where you can have some relationship going on, okay, and then start from there. So if you go into physics, okay, in a way it's physics and it's also geometry, okay, whichever way you want to see it. So you see, I will tell you how it is physics and how it is geometry. See, if you look at it from the geometric point of view, you see you think of this curve gamma as being traced by a moving point. Okay, so there's some moving, so it's a curve, okay, and so this curve. What is the simplest curve that you can think of? It's a circle, okay, and you see that is why we think of the circle is, you see, I want to quantify curvature. So first of all, I need a formula for curvature, and I want to first look at the situation when curvature is constant. Think of a curve that is curved the same way at every point. And what comes to your mind? Only a circle. Okay. So the circle is the most natural thing that you can think of. And the circle, you take any point on the circle is curved the same way at that point as at any other point. So the model for a constant curvature is a circle. So you see, it's a circle, it's centered at some point O and some radius R. So this is the simplest model. And you take any point on the circle, whether it is P or Q or some R or something like that. Let me not use R. Let me use something else. S. The curvature at P is the same as the curvature at Q is the same as the curvature at S. At all these points, the curvature is the same. And how do you say that? I mean, if I take a portion of this arc here, and cut it and try to superimpose, I can correctly superimpose it here, and I can also correctly superimpose it here, and that tells you that it's really curved the same way everywhere. Therefore, you see, this circle is the model for constant curvature, okay, but still this doesn't give me a formula for curvature. It says that, okay, constant curvature comes from a circle, all right, but now what is curvature supposed to be? It's supposed to be the degree to which the curve is curving. And now you can think about how this circle is going to look. How can I make its curvature small? Can I make its curvature large? And you can see something here. You see, if I make the radius large, okay, the circle will become very big, and an arc of the circle will become flatter. Okay, whereas if I make the circle very small, okay, it's very curved, okay, and therefore the curvature will go up. So what you can see is that if I draw another circle here, suppose I draw a large circle here, okay, and this has some center somewhere, and it has some radius r dash, okay, you can see that the curvature of this circle, if I call this circle as C dash and call this circle as C, curvature of C dash at any point P dash is, the curvature is strictly less than the curvature of the circle C at the point P. Okay, this circle is flatter and this circle is more curved. So the curvature of this is less and the curvature of this circle is more. You agree with this, right? So from this, what is it that you see? What you see is that you see the curvature, what happens to the radius? You see, for this circle for which the curvature is large, you see the radius is large. And for this circle for which the curvature is small, the radius is small. Okay, so smaller radius gives you larger curvature. Okay, and larger radius gives you smaller curvature. So you infer the following thing, that the curvature is seemingly inversely proportional to the radius. Okay, so you get that idea. So you see, curvature is inversely proportional to the radius. At least for a circle, this is quite believable. All right. The more the radius, the circle becomes flatter, and then 1 by that, you see the curvature becomes small. Okay, and that agrees with the curvature becoming smaller. Of course, if the radius goes to infinity, what happens? You can think that your circle with infinite radius, the center at infinity is a straight line. You can think of it as straight line. And a straight line, for a straight line, what happens to the curvature? Curvature becomes 0. Okay. So you see, infinite radius gives 0 curvature. So you can see very well that this is a very nice relationship. So what do you do in mathematics? You start with this, and then you say, whenever two objects are related, whenever two variables are related, you put a constant of proportionality. So you write curvature is equal to some constant by radius. Okay. So you put this, and then normally what we do is that we try to put that constant as 1 for simplicity. So this you put constant is equal to 1, and you write curvature is equal to 1 by radius. Curvature of C dash is 1 by R dash. Okay, and curvature of C is 1 by R. And 1 by R dash is certainly lesser than 1 by R. That's because R dash is greater than R. It agrees, right? So this is one level of mathematical, very simple mathematical proportionality that's working, that you have formula. But what does it do? Mind you, it's a very simple case. It's only giving you for this model of constant curvature. Okay, so we have agreed that if you have a model for constant, the model for constant curvature is a circle, and the curvature of the circle is given by the reciprocal of the radius. The smaller the circle, the smaller the radius, greater the curvature. The larger the circle, the larger the radius, lesser the curvature, it's more flat. Okay, right? Now, let us look at it from, so this is if you are looking at, something that has constant curvature. All right. But if you look at a curve like this, okay, the curve is it's not a circle. Okay, if you're looking at a general curve, the curve is turning. At some points, the curvature is high. At some points, the curvature is low. Okay. Now, how are you going to deal with that situation? All right. So what you do the following thing. If you think about it, the idea is that at every point, what you can do is you can try to approximate the curve to a circle. Okay, so what I'm proposing is that suppose you have a curve like this, and let us say you have a point here, let me call it as P. What you can do is that you can, draw several circles which touch this curve at P, and try to find the best, the closest circle that is closest to approximating the curve at the point P. Okay. Yeah, again, I think the video has frozen for some reason. Yeah, Krutarth, is he around?
Yeah, just a second. You should be able to see it now.
Let me see.
Yeah.
Yeah, I can see. Right. Okay. So, I mean, Yeah. So if anybody has any questions, please don't hesitate to ask. Okay. So you see, as I was trying to tell you, this idea that the curvature of a circle of radius r is 1 by radius, it's something that's very natural. Okay. And what we are trying to do is, just excuse me for a moment. ஏமா anything இல்ல நான் ஒரு லெக்சர்ல இருக்கேன். Okay, sorry for the distraction. So you see, let me sum up what we have done. We have agreed that you take the model for constant curvature as a circle, and the curvature of the circle is reciprocal of the radius. Okay. Now what we want to do is to look at a curve which is not a circle. Okay. That means, it's curving. At some points it's curving more, at some points it's curving less. So what are you going to do in this situation? So what you do is, so here is a curve gamma. I've taken a point P. At that point P, I want to calculate what is the curvature at P of gamma. I want this. How do I do this? So the idea is that you try to use this model of a circle and try to find a best fitting circle to the curve gamma at the point P. So what does that mean? It means, you see, what you do is at the point P, there is going to be a tangent. There's going to be a tangent. This is tangent to gamma at the point. So let me write at the point P. Okay. So I'll just write t gamma P. All right. And this tangent line, now once I have this tangent line, what I can do is I can draw several circles, which touch the curve at the point P. So, what is this idea of two curves touching at a point? It means they have common tangent. All right. So when one of them is a line, you're just saying that the line touches the curve. Okay. So what I'm going to do is I'm going to draw, several. So let me draw it in different colors. So I will use, let's say, orange. So I can draw a circle like this. Okay. And then, I can draw another one, maybe a pink one. Oops. We draw an orange one. Okay. And then maybe, let me draw one more, maybe green one. Okay. So, I could do this. I could draw these guys on the other side also of the curve. Okay. And if you go very closely and look at it, okay, mind you, the red one is the red curve is the given curve. Okay. The green, the orange, and the pink, they are circles I have drawn at that point. And you can see that, well, the green seems to be a better, approximation to the curve than the orange or the pink one. Yeah. The curve is red in color. Do you agree with that? Okay. So you can, at least visually, you can see that if you adjust, I mean, what is the difference between all these things? It's their radii. So you see the green one has, its center somewhere here, and its radius is something like this. Okay. And if you had taken the orange one, it will have its center somewhere here. And then if you had taken the pink one, it's going to have the center somewhere here. Okay. So you see the radii are changing, and you can believe more or less that, if you kind of draw a very big circle, okay, then it's not going to, it is not going to, it is going to flatten out more than the curve. For example, suppose I drew a curve like this. So let me show you something. Let me use this color. Let us say. See, suppose I drew such a big circle like this. Okay, I think I just, so let me, suppose I draw something like this. Okay, you can imagine that this is a very large circle. Okay, the one that I'm drawing in blue. What is the problem with this circle? Its radius is too large. Okay, and it's not matching the, mind you, the original curve I want to approximate is a red one. Okay, so what is the problem with the blue one? The problem with the blue one is that its radius is kind of very large. Okay, So what this means is that, if you start drawing circles that touch the curve at the point P on the right side, mind you, I'm drawing everything on the lower side. If I draw it on this side, it certainly none of these is going to match. That is, if I take the mirror image of each of these circles by that tangent line, those will also touch this curve, but they are on the other side and they are not going to match this red curve even closely. Okay, so the moral of the story is I should not draw on this side. Okay, I should not draw on this side. I should draw on this side. And if you draw the radius too small, it doesn't fit. If you draw the radius too large, it doesn't fit. So there's some intermediate radius which kind of should be the best fit. So what this tells you geometrically is that you should expect that there is a particular circle. You should expect that there is a particular circle, only one unique circle, which is tangent to the curve gamma at the point P. All right. That means, the circle will also have the same tangent as the curve gamma at the point P, and its radius is the best possible, so that the small piece of the circle close to P will best approximate the curve gamma. So can you believe that from this? So the moral of the story is that, you should expect this. So here is the definition. The definition is that it is the reciprocal of the radius of the best fitting circle, so gamma at P. So and why are we doing this? Because we agreed that, for a circle, the curvature is one reciprocal of the radius. So what you're doing is, so your model for curvature is the curvature of a circle is reciprocal of the radius. So that is your model. And what you're doing is, when you have a curve such as gamma, okay, the red curve, you at a given point P, what you're doing is you're trying to find a best fitting circle, okay, and for that circle you calculate the radius, take its reciprocal, and that will be the radius of curvature at that point. Okay, so this is a very believable and geometric thing. And why is this believable? Because you see, if you take circles which are too small, they don't fit. Okay, and if you take circles which are too large, also they don't fit. So something in between, there should be something, by continuity, there should be something in between that will fit best. Okay, all right, because these radii are increasing. So there should be some particular radius for which this, if you draw the circle at the point P, which is tangent to the curve, which means it has a same tangent line as the curve at the point, then that should be the best fitting circle, right? So this is very believable, right? Now, so the moral of the story, so I will just write it. So you see, this is what mathematics is about. Geometrically, you see something happening, you postulate that this should happen, and then you will need to justify it. So you see, this is how the idea is built. So what I'm going to do is I'm going to do the following thing. I'm going to write this. I'm going to say that, so let me put it in black. So let me put something like this. Like this, I'll say. So there is a best fitting circle, center tangent. Sorry, let me write it. Tangent. Oops. Tangent to gamma at P. Okay, and I will. So there is a best fitting circle tangent to gamma at P, and I will call this as C gamma P. Okay, and this C gamma P is the best fitting circle, and this best fitting circle has a, it is going to have a center, and that will be, I will call this as C of P. Okay. And so this is center of C gamma P. Okay. And there is going to be this radius. I'll call this as R sub P. Okay. So because everything depends on the point P. So you see, so that means that this distance, okay, this is going to be R sub P. And and this is going to be the radius of curvature will be 1 by R sub P. Okay. And what is this R sub P? R sub P is just the distance between P and C of P. It is this distance from the point P to the point C of P, which is the center of the best fitting circle. Okay. So this best fitting circle has a name. So now you see, I believe that this should be true. All right. So you see, what I want you to understand is that the great thing about mathematics is the genesis of things. Okay. When you people read mathematics or physics or whatever it is, see, you usually the way things are taught and things are learned, you see a book, you see some book, there is a definition. Okay. And then there are some examples, and then people start using those definitions to derive formulas and write formulas and theorems and things like that. I'm always worried about, if you want to really enjoy mathematics, you should do the following thing. You should ask yourself, where did this definition come from? I mean, what is the reason for this definition? I mean, that's what makes you to really enjoy mathematics. Okay, what is the reason for such a definition? Where is the motivation for this definition? Why is this definition natural? Can you relate it to something that you see in life, which makes you believe that this definition is reasonable? And when I say see in life, it means that can you relate it to something that you see in physics, or do you see something in phenomena of nature, or something you see in geometry? Okay, you have to think like that. Okay. So in fact, the truth is that all these things, when they were, if you go back to the history of mathematics, all these things came up by very natural, in a very natural way. Okay, and all these things have had a few hundred years of existence. But what you are getting is a Maggie 2 minute instant Maggie noodles kind of thing. Okay, everything is being cooked up in a book, and it's just being thrown at you, and you're just lapping it up, gobbling it up, without really appreciating what's going on. Okay, so I want you, if you want to really understand mathematics, you want to enjoy mathematics, you should go back one step and say, where did this definition come from? You should ask yourself that question. Why should I believe in this definition? Give me a natural reason. Okay, so if you look at it like this, from the geometric point of view, there appears to be a best fitting circle with which has a center and a radius, and the reciprocal of the radius can be called the radius of curvature of the curve at the point. And now now you can see something very nicely happening. You see something that we already saw. If you took a curve like this, you see, if you took a curve like this that I originally drew from this gamma, at this point the curvature is more, because the best fitting circle is going to be very large. You see, the best fitting circle will be like this, if you want. At this point, the curvature is going to be, at this point, so let me repeat that. You see, if you take the point P, okay, if you take the point P and draw the best fitting circle, okay, you're going to get a very large circle. So let me try it. I'll get a very large circle. In fact, even this is very bad. I perhaps get something very, very large. So if I try to draw it, it will be like this. So I have to draw something that's very close to the curve. Okay, that's what best fitting means. So I have to, of course, my pictures are not great, but nevertheless, let me try. So you see, I'll get a circle like this, and you can imagine that this circle is going to be pretty large. Okay, and this is a circle to gamma at P. This is the circle of curvature, and you can guess that its center of curvature will be somewhere here, if you want, something like this. And this will be the radius of the curvature at P, and therefore this curvature will be 1 by RP. And you can see that this circle is large, this RP is large, so 1 by RP is small. That's why this is small. Okay. On the other hand, if I took this point Q and try to draw a best fitting circle, I'll get a small circle. Okay, and you can see that there, the curvature to gamma at Q is going to be small. This circle at the circle of curvature at to gamma at Q is going to be small. The radius of curvature RQ is going to be small. So 1 by RQ is going to be large. So you see this 1 by RQ is that's why larger than 1 by RP. So you see it agrees with what we intuitively thought about, right? So this works. All right. So this is a very, very nice, is a very nice thing. And again, this brings us to the next question. And what is the next question? As a mathematician, the next question is, well, you're now saying that at every point there is a best fitting circle. It's believable, but prove it. Okay, because mathematics doesn't work without proofs. Krutarth, I think again my video has frozen. I wonder why this is happening.
Yeah, we're sorry about that, but okay. Yeah.
Again.
Yeah, can you check again now, please?
Yeah.
Yeah, we're sorry for this, but there seems to be some Wi-Fi issue. Yeah, okay. Now I can see everybody. Yes. I mean, if I can't see students, then I am kind of demotivated. I
Okay.
understand. Thank you.
So psychologically, you see, if I see some faces reacting, then it gives me feedback. Otherwise, it's like talking to a wall. All right. Yeah, I'm sorry I'm unable to be there physically, but we can use technology to our advantage. So you see, so therefore, so let me repeat the question. So the question is, you see, okay, we have done two nice things. We have taken the model for constant curvature as a circle, and we have agreed that the curvature of the circle is the reciprocal of the radius, which is very nice. And then how do we tackle the case of a general curve? We say that you give me any general curve and give me a point on a general curve. At that point, there is a best fitting circle. There is a best fitting circle at that point. Okay, take its radius and take the reciprocal of that, and that's going to be the curvature. Okay, so what does, as a mathematician, what would I say? Okay, come on, all your intuition is great, now you prove it. I mean, if you can't prove it, then this is something that I'm not ready to accept. See, because mathematics, that's the problem with mathematics. The problem with mathematics is that you need to give proofs. So for example, lots of things in number theory, very simple things like rollback conjecture. Every even number greater than 2 can be written as sum of two primes. That's open. Okay. Twin prime conjecture, that there are two primes separated by 2, no matter how far you go in the list of primes. Okay, just like 11 and 13, 17 and 19. Okay, no matter how far you go down the list of primes, there are always 2 primes. The distance between them is 2. Okay, there's a twin prime conjecture. So you see, these are all basic questions which are still open. So you see, mathematics, unless you prove something, it's open. Okay, so nothing works without a proof. So I'm asking this question. All right, all this is great. Now prove to me that given a curve and a point on the curve, there is a best fitting circle. How are you going to get it? How are you going to get it? All right, that's the question. And again, you see, the beauty of mathematics is that, the beauty of geometry and mathematics is that you can get it. All right, if you think about it sufficiently well. Okay, so incidentally, let me give you the terminology. This best fitting circle is given a name. It's called osculating circle. It's called osculating circle to gamma at P. It's called the oscillating circle, and it's all, the other name is also, it's also called circle of curvature. So it's called the oscillating circle. And the center of that circle is called the center of curvature. Okay. And of course, this radius is called the radius of curvature. Okay. And once you have all this, the curvature is just the reciprocal of the radius of curvature. All right. That's how things go. So what is the question now? The question is, why does this oscillating circle exist? Okay. By the way, the word osculare means kiss in French. Okay. And basically what it means is that the circle is the best fitting circle to the curve. So it's kissing the curve. Okay. So that's the French language there. Okay. It's a best fitting curve. So if you take the oscillating circle and the curve very close, it's like two lips kissing. Okay. So that's why it's called oscillating circle. All right. So fine. So the question is, how do you get this oscillating circle? How do you get this circle of curvature? Why should it exist? Okay. So here is, so let's try to, so I'm still using only geometry and I'm trying to explain. So I'm going into the geometry part. That is an explanation that involves physics. I don't know whether I'll have time to do that. I'll try to quickly tell you about that. Then there is an explanation which involves calculus and so on and so forth. But I'm just trying to explain some, some ideas, all right, given the time that I have. So the question is, we ask this following question: existence of oscillating circle. How do you show this existence? So you see, the idea is the following. So what is our problem? Our problem is we have a curve gamma. We have a point P on the curve. Okay. And at that point P, you want to find the best fitting circle. All right. Now, you see, just think about it for a moment. Let me draw, we will do some, back calculation. Suppose there was a best fitting circle. So it's going to be, so let me draw something that is, let me draw more curve so that I can, it looks somewhat realistic. So, let me draw something like this. Okay. So I take this as my point P, and let me draw the best fitting circle. This is the red circle. Okay. So this is the circle of curvature to gamma at P, and it has a center. So this is the center of the circle of curvature. Okay. And this is going to be the radius of curvature at P. And what do you know from geometry? See, from geometry, you know that if you draw the tangent to, so this is my, mind you, this is the tangent to gamma at P. Okay. And then, of course, let me also mark gamma. Gamma is this blue thing. That's my curve. Okay. And the red one is the circle of curvature at P. All right. And mind you, there is something that you can see. This blue curve gamma and the red circle of curvature, they both have the same tangent, because that's what it means to say that the circle of curvature is it touches the curve. When do two curves touch each other? If they have the same tangent. Therefore, this tangent T gamma P should be the tangent to both the circle and the blue curve, the red circle and the blue curve. What does it mean? It means that you see this PCP, that will be the normal, right? The radial line is always normal. So that means this angle is 90 degrees. All right. So see, you have to show that the circle of curvature exists. That is the same as trying to show that the center of curvature exists. Okay. Because to find a circle, you need to define a circle, you need a center and you need a radius. Okay. But you see, the circle, the circle is tangent to the curve at that point. Therefore, the center will always lie on the normal to gamma at P. So you see, this is one thing that you get from geometry. The center of curvature has to lie only on the normal line. So you take a curve, take a point, you draw the normal line, and the center of curvature is to be found on the normal line. All right. So that is one clue to find the center of curvature. But you see, this solves the problem. If you show that the center of curvature exists, that is, if you are able to show that there is a point on the normal line, okay, then you take that. If you get that point, then its distance from the given point will give you the radius of curvature. So you see, I'm trying to motivate the following statement. To find the center of curvature, you have to look for a point on the normal line. Okay. Now the question is, why should such a point on the normal line exist? Okay. Yeah, I see some discussion going on there. If you have any questions, you can also ask me. You have a question? So Krutarth, you can is there a way for me to
Thank you. So, but
I can't see you. Can you come to the front side? I can see only I can only see yeah, now I can see you a little bit. Yes. Yes. Hi. Yeah, great. Yeah, tell me. Yeah, tell me. What's your name? Please tell me.
So if we take two circles,
Yeah.
a tangent to each other at a point, and then we have a curve which touches both of the circles infinitely many times and then passes through the point, then that would have two different circles. And if we make them different radii, then it wouldn't necessarily have a certain radius.
I mean, I don't understand what you're saying. I mean,
If we
you're saying that if you take a point on a curve and take the tangent, and you're saying you can draw many circles, right? That's what you're saying,
no,
of different radius.
trying to give a counter example. So if we take two circles and then we draw a curve which passes through the two tangent circles, and then we draw a curve through their intersection, and then it touches both of the other curves infinitely many times, then
Infinitely. So let me try to write out what you're saying. You're saying take, I'll draw one circle like this, and then you're saying draw another circle like this. Is that what you're saying?
yes.
So I have this common tangent here. Yeah.
So
Now what do you want to do?
so then the curve will touch both of the circles infinitely many times.
Wait. Where is which curve? Which is the curve you're talking about?
The
Where is
curve
the
is constructing.
oh, oops. I lost. Why did I lose? Cancel. Something happened. Wait. Something happened. Again, your video has frozen. Are you able to hear me? Let me try.
Okay, so first it touches one circle, then it touches the other circle, and then and then it goes closer and closer to the tangent point, goes through the tangent point, and then comes out on the other side and does the same thing. So then, how will we know which of these is the circle of best fit?
No, Krutat, I can't see anybody. Oh yeah, now I can see. Right, yeah. No. See, I don't understand. What do you mean by? See, if you want me to draw a curve that touches both these circles, I will draw something like this. Okay. So I will draw something like this.
Yes.
I can draw something like this, right?
Yes.
Yeah. So that's one curve.
Oh.
What do you want to do?
So first it should touch one circle and then it should go to touch the other circle and then back and forth.
Wait. Now. Oh, see, I think you're getting confused with something. See, what do you mean? You're saying it should touch one circle, but not the other circle at the same time? Is that what you want to say?
Yes, I think there's a diagram on the.
No, if you want, can you draw the diagram that you're talking about and show it to me so that I can explain?
Yeah,
See, what I want you to understand is that there is a curve that is given to you. There is a curve passing and a point on it.
yes, I think on the.
I think your video is kind of stuttering and it's very grainy, I think. Kritak, do you have is it a good quality internet connection there? I can see only stuttering video. Or is there some network issue? Are you people able to hear me?
Okay, so I guess I could give an explicit example. So we could take square root of 1 minus x square comma sine of x squared sine 1 over x. No, no root. Wait. Okay, we could take the curve of x. No, 1 minus x comma root 1 minus x squared times sine of 1 over x.
You're trying to take a curve which is like the topology sine curve, which is wiggling a lot, right?
Yes, so we could take a curve from minus 1 comma 1 to R2.
See, no. See, I think you're confusing. I think you're confusing some things that you've. See, I'm looking at a particular curve or a piece of a curve that's passing through a point. Okay, there's only one piece of the curve passing through that point.
Yes, no, I'm saying I guess I'm the curve from minus 1 comma 1 where we take x to x comma 1 root 1 minus x square sine of 1 over x.
Okay.
So yeah, that would have the circle, one circle above and one circle below it, which both of which seem to be both of which seem to be equally valid.
No. So you see, I unfortunately we are still, our I can't. Yeah, your video is terrible. I mean, yeah. If somebody has a tablet or something on which you can write and show it to me. No. See, don't take. No. See at the point where it gets flattened. You see. Okay. So yeah, I understand. So let me tell you something. So you see, what's your name? What's your name? Hello. Can you hear me? Hello.
Yeah, he's writing something. Okay.
No, so,
Ah.
yeah, no. So I want to say the following thing. See, there are, at least when we are talking about curves and all that, okay, we are assuming that things are sufficiently smooth, okay. We are not looking at some, topological, some things that have pathologies with respect to, differentiability or topology, okay. For example, I'm not looking at fractal curves or, some crazy curve like the topology sine curve. I'm not looking at anything crazy. I'm looking at something that's natural, okay. So uh, you must understand that when we approach science or mathematics, we first look at the simple decent looking cases and try to develop the theory for that. Then what happens is that then you start, you will see that when we do all this, when you start differential geometry like this, you have to assume that the curve is at least second continuously differentiable, okay, at the point, and in a neighborhood of the point where you want to do all this, you should assume that the curve has a second derivative which is continuous, okay. Now your function will have a problem. It'll have a technical problem at that point, okay. So it will not work for your function. So it's yeah, the approach to mathematics must be that first look at the simple cases where you get nice things, and then come to extreme situations like the one that you are trying to think about, okay.
Thank you.
Yeah, sure. So you see the so let me I think the video is really bad. I'm only seeing roughly 2 frames per second. So you see, you, for continuity of motion, you should have 30 frames, at least 25 frames, 24 frames per second. Okay, I can see only 2 frames per second. So it's like one of these old movies uh, about from about 100 years ago or something like that. Yeah, okay. So see that question that your one of your classmates has asked is a very relevant question. The important thing is that you see that is an extreme situation. There are curves which are crazy, all right. They can be topologically crazy, like space filling curves, okay. You'll be amazed to know that there are things called piano curves, and these are curves that can fill space, okay. When piano invented it, people got crazy, okay. I can use, and what's a curve? A curve is just a continuous image of a line, okay, continuous image of the real line. And people couldn't believe that I can have a continuous image of the real line and fill up 2 space, 3 space, even n dimensional space for any n. And piano invented that. So these are the curves which are called piano curves, and they are absolutely topologically crazy ones. And there are also curves which are crazy in the sense of calculus. So you can find a curve that is everywhere continuous but nowhere differentiable, okay. So the things like the Volterra curve or Volterra function, okay, these are all fractals. So these are extreme pathologies in topology and in calculus differentiability. We don't think about that. The approach should always be, you think about nice situations, develop the theory for nice situations, try to see what works, and then you first treat the nice situations and then go to the extreme situations. Don't start with an extreme situation. If you start with an extreme situation, you will get stuck. You'll not know how to attack it. Always start with the simple situation, okay. Try to work out the theory for that, and then when you work out the theory will dictate what are the conditions you have to put. So you will see that if you want to develop this kind of theory of curvature, you will need second continuous differentiability, okay. Which is what is called a C2. You need second continuous differentiability. If it is plane curves, if it is space curves, you need C3, which means third continuous differentiability. Okay, and then you can develop a decent theory of curvature. And the question is that what happens if this differentiability is affected? Then you get all these pathological examples like the one that you said. Okay, so that is that is not something that you should think about at this point. When you are trying to do something, you should think of a nice general situation and develop the theory. So that's how I'm thinking. Okay, so I'm not thinking of pathologies. All right. So I hope that reasonably answers your question. Okay, so let me come back. So the question is, how are we going to show that there is this circle of curvature? And mind you, to find the circle of curvature, I have to only show that there is a center of curvature. Because once I know the center of curvature, I know the circle of curvature. Why? Because I have to just draw the circle with that center, and radius being this radius, which is the distance of that point from the point on the curve. And I have one clue where the center of curvature will lie. It will always lie on the normal to the curve at that point. Now the question is, how do I locate it? So here is where some geometry works. So what happens is, the following thing happens. You take the curve, gamma. What you do is that this is my point P. At this point, I have the tangent to gamma at P. Okay. Then at this point, I also have the normal. This is normal to gamma at P. And I know somewhere on this line, somewhere, I don't know where, somewhere on this line, the center of curvature is going to lie. I have to locate it. How do I locate it? So what I do is, I again use a little bit of intuition. You see, the curve, if the curve is curving in a nice way, then the curvature should also be continuous. That means if you, as you move the point, the curvature, which is a function of the point, it should change continuously. So that means that curvatures of nearby points should be close to the curvature at the given point. Okay, and how do you get the curvatures of the nearby points? By again looking at the centers of curvature of the nearby points. And where are they going to lie? They are going to lie again on the normals of the nearby points. So that's the clue. So what you do is, you do the following thing. So you see, what you do is, you take the following thing. Let me get rid of this. So what you do is, you take two more points if you want. I take a point here, P dash, okay, nearby point. And what I do is that I draw the normal at that point. So I draw, this is the tangent to gamma at P dash, okay, and then I draw the normal there. Okay, that goes and hits somewhere here. All right, and this is the normal. So let me write it on this side. And let me rub this out. Now, so this is normal to gamma at P dash. Okay. Then I take another point on this side if you want. I'll take a point here. I'll call this as P double dash. I draw the tangent there. So this is a tangent to gamma at P double dash, and I draw the normal there. So you can guess I will get a normal. Okay. And you see, that normal also hits the. So this is normal to gamma at P double dash. Okay. Now you see, I get these 2 points. I get this violet point, which is the point of intersection of the normal to the curve at the nearby point P double dash, and I get this blue point, which is the intersection of the normal to the curve at P dash with the normal at the given point P. Okay, so I get these 2 points. And guess what? You should expect that if I let P dash to tend to P, if I take a limit, okay, then this this point, if I call this blue point as let me call this as something C of P dash. Okay, I should not call it a CP dash. Let me call it something. So again, I lost video. Yeah, okay. So I can see you all again. That's great. So you see, what should you expect? You see, as if P dash goes to P, okay, then this point, let me call this as, I have to give it a name. Let me call this as D dash of P dash. As P dash goes to P, D dash of P dash should go to, the center of curvature at P. And as the same thing should happen if I move P double dash to P, okay? If I move like this. So as P double dash goes to P, you should expect that if I call this point as D double dash of P double dash, this D double dash of P double dash, that should also go to the curvature at P, okay? So what is the moral of the story? The moral of the story is that if you take a given point and you draw the normal at that point, and you take a nearby point and you draw the normal, these two will intersect. You get a point of intersection. As the nearby point comes to this point, okay, this point of intersection, you expect it to go to a limit. Okay, now it's very, very funny. If so, I took P and P dash and P double dash because I wanted to say that there are I'm taking points on two sides, and I'm taking the normals there. Okay, but you could have just done it with just one on one side. So all I could have done is I could have taken the curve gamma like this. This is the point P where I want the center of curvature. So I draw the tangent to gamma at P, and this is a normal to gamma at P. And then what I do is I take a nearby point P dash, okay, and I again do the same thing. I draw the normal there, okay, and this normal goes. So this is the normal to gamma at P dash, and they hit at this point D dash of P dash. Now you see, you just think about it. This is 90. This is also 90. There is a tangent here that I am not drawing. Okay, let me remove it. Okay, you can see that if P dash goes to P, okay, then this normal at P dash is going to go to normal at P. Okay, and what do you think is going to happen to this point? Now, there is one crazy thing that can happen. This point can just go away to infinity. Because after all, these two normals are coming closer and closer. They becoming parallel, right? So there's one thing that this point may escape to infinity. This may just disappear. Okay, if that happens, then we are in very bad shape. Okay, because if you take two parallel lines, as the lines become parallel, the intersection point goes to infinity. You can expect that. And as P dash goes to P, the normal at P dash becomes more and more parallel to the normal at P. So you expect that this point may just fly away. Okay. But actually it doesn't. That's the amazing thing. As P dash goes to P, this point doesn't go away. It goes and stops somewhere. And where it stops is exactly the center of curvature. Okay. As P dash tends to P, D dash of P dash tends to a particular limit, a point CP on the normal to gamma. So you see, this as P dash goes to P, the normal at P dash and the normal at P, they become parallel to each other. So the point of intersection doesn't fly away. It goes and finally stops somewhere. Okay. Now, so here is something that's happening. You see what is happening here? What is a new element that has come in here in our arguments? Can anybody see that? I mean, noticing these things is exactly the joy of mathematics. So what is it that you see? Yes. Yeah, please.
Yeah. Sir, I wanted to say something like I was
Yeah,
thinking.
I mean, you can just come into one of these front chairs and sit down so that I can see you also. That'll be nice. At the moment, I can't see you. Yeah, sure. Yeah, please.
So, like, you can, clearly the center of curvature will lie on the normal, right?
Correct.
And you basically need to find the radius of the curvature to locate the center, right? And if you basically try to back calculate, this is a back calculation only. Like, I'm assuming the curve to be twice differentiable with respect to a suitable x-axis. Um, if you estimate the radius to be like r d theta, where theta is the angle made by the tangent with the x-axis. The angle made by the normal will also be the same d theta, right? Like the two normals. So then the length of that arc is r d theta, and you can write that as under root of like dx square plus dy square, right? Or and like if you like do the arithmetic, then you will get radius as a function of y dy by dx and d2y by dx2, and then you can just locate the center of curvature on the normal using.
Yeah. I mean, you're giving the usual. This is the calculus derivation, right? That probably you see you're undergraduate.
No, sir, I'm actually in 11th grade.
Yeah. So you see, so you must have seen this. So my question is, no, that's okay. Say this is whatever you're saying is available in, I mean, in standard textbooks. Okay. It's not about that. The question is, where did all that come
Sorry?
from? The question is, see, all this stuff is in books. I mean, whatever you're saying, see, the formulas are there, then calculus is applied, and then there are many ways of deriving this. But what I want to insist is, I mean, where is the starting point? Where is the starting point? So I'm saying, you see, at this juncture, for example, have you noticed? See, so far we have been looking at it geometrically, but a new element has come in. Can somebody tell me what that element is? There's something that has sneaked into our discussion. See, so I've been talking about geometry only. So far, I've only used geometry. I've used circles, tangents, normals. All right, but there's a new. Can you see? There's a new thing that I keep that is sneaked into our argument. I mean, it is also the reason why. I mean, whatever you said is right. The question is why? Why did all that have to be done? See, noticing that is I mean, that joy is in noticing why you're doing what you're doing.
Yeah, I think one of the things is ki matlab, like P, like the center of curvature can be done quite nicely using the geometrical construction of taking P dash quite close to P, and the limit, then you get the, like in the limit of P dash going to P, you can get a center like on the.
Yeah. So what is it? What is it that is sneaking in? What does it mean? What's going on?
I think what do you mean by sneaking in?
No, I mean, what? See, there's some mathematical concept that's being. You said it, or you almost said it. I mean, you said it actually, but you realize. Uh, you said limit, right?
Limit, yes.
Yes. So you said limit is the limits are coming in, right?
Yeah.
And since limit, so you see, the point is that you say I use this p dash going tends to p, okay, this tends to. So you see, what you must understand is limits are coming into the picture, all right, and you are dealing with normals and tangents. Tangent has got to do with the derivative, right? That
Right.
when you take the slope of a curve, the slope of the tangent is exactly the derivative at that point, right?
Yeah.
So if you want to keep track of the normals, keeping track of the normals is the same as keeping track of the tangents, right?
Yeah, because I make a fixed angle of 90 degree.
Yeah. So either you keep track of the tangents or you keep track of the normals is the same thing. But keeping track of the tangents has got to do with keeping track of the derivative, right?
Right.
So you see, therefore so you see what you're trying to do. You're trying to take limits of the first derivative, okay,
Yes. Mm.
and that should essentially be a second derivative, okay,
Yeah.
because you want to know how much the first derivative changes, and that's like the first rate of change, the first derivative, so it's the second derivative. So I'm just trying to say that from this very geometric thing, you can see already the second derivative is involved. Calculus. So I just wanted to say that what sneaks in at this point is calculus. Okay.
Right.
So what sneaks inside is calculus. So calculus has sneaked into our geometry. Okay. And now you see whatever you said can be done. Or you're trying to say that in polar coordinates. Okay. You're trying to use r and theta. But
Yeah.
you can as well use xy coordinates. What you can do is you can actually write down the equations of the nearby line and use calculus. Okay, so you can take this, you can write gamma as a so now you see you will have to again formalize. What you have to do is that you write gamma as gamma of t, where t is a parameter, and a t equal to t naught, you get gamma of t naught is the point p naught. Okay, I mean if I want to call this as p naught or p, so if I call this as p naught, then this is a tangent to, let me remove this. Okay, and this is going to be normal at gamma at p naught, and I should put p naught everywhere here. Okay, you will have to parameterize your right gamma t as xt comma yt because it's 2 points. Then what you have to do is that you can write the equation of I can write the equation of this normal at t naught, and you can write this equation of the nearby point. How you write this nearby point? You'll write it as gamma of t naught plus delta t. That's a nearby point, and if you want this p dash to go to p naught, you have to just let delta t to go to 0. And this gamma of t naught plus delta t, again, that will allow you to write the equation of the normal here. You get two straight line equations. If you solve them, you will get this point, and this will be a function of delta t. And if you are clever enough and you let limit delta t tends to 0, you will get the center of curvature, and that's exactly the derivation.
Right. Yes.
Yeah, that's exactly what you said. So I see what is interesting is that you see how you start with something geometric, and you see that the geometry itself gives you the roots of calculus. Okay, and if you try it like this, you will get the formula for curvature. You can prove that there is a circle of curvature. You can prove that there is a center of curvature. Okay, and once you do that, you see that is kind of a complete mathematical theory. All right. So this is the physical. I mean, this is the geometric and calculus point of view. All right. But there is something more that has to be worried about, and I'll tell you this. I mean, this story goes on. The thing is that when I try to parameterize this curve as gamma of t, you see the same curve can be parameterized in many ways. Okay, so you may be worried that if I change the parameterization for the same curve, will the formula I get be based on the parameterization? It should not be, because curvature is geometric. So you have a job to do. You have to show that if you change the parameterization also, you see the curvature formula that you derived, the circle of curvature, the center of curvature, the radius of curvature, formula for the curvature, all those things should not depend on the parameterization. You have to show that.
So basically, like if you substitute x and y again, this should basically remain the same. That's what you're saying.
No, I'm saying that when we do all this calculus, you have to write gamma as a function of t.
Right.
And there are many, you can write the curve, you can give different parameterizations for the same curve. Whereas you see, that means you're changing the function, but the curve that is being traced is not changed.
Right.
Right? But the problem is that if you change the function, this derivation depended on that function, right? So you have to worry about whether the curvature formula you're getting is going to depend on that or not. It should not, because curvature is geometry. All right. So therefore, this is again. So this brings up more mathematics. So what it will bring up is, if you really look at it, it will bring up this mixture of results, which is this nexus between the open mapping theorem, the implicit function theorem, and the inverse function theorem. These are theorems in advanced analysis that will come into the picture if you try to explain that point of view. You want to reconcile that point of view.
Yeah. Yes.
Yeah. Yeah, Kritarth, how much time do we have? I mean, I have, I don't know. I
I think we don't have more than 5 minutes, if that's fine.
Yeah, so yeah, again, I think your video has frozen. Okay.
Ah,
Yeah, so
the Wi-Fi seems to go periodically.
I thought CMI, uh, your Wi-Fi is not good there.
It should be working now.
Now it's back now. Okay, all right. So you see, so I will tell you, so at the end of all this, there's a lot of mathematics to be done. Okay, and I'll give you a reference book where you can read. I mean, people even from school can read up all interesting things. And here is a reference book. This is Presley, Elementary Differential Geometry. Okay, so you can look at this book. That's the book I will recommend for that's accessible to anybody, even 11th standard students who know a little bit of calculus can understand that. Okay, you can look at that book. So I mean, so the story goes on. There are lots of things that can be done, and I leave you at this point, trying to convince you that see, please understand that formulas that you read now, they have come over a period of time, and people have thought about them in a very natural way. And somehow, we what we do in these days is that we quickly learn definitions, theorems, formulas, without even understanding what was the motivation, original motivation. So that is something that you should ruminate on if you want to really enjoy mathematics. Okay. And so the motto of today's talk is, if somebody gives you a definition, you should say, where did this definition come from? Give me a motivation as to why I should believe in this. All right. And try to discover that. Okay. I think that's one way of enjoying mathematics. All right. So I will stop here. Okay. If anybody has any questions, please ask me. Thank you for your patience. I think several other people have already disappeared. I think.
Thank you for the talk, sir. We are sorry for the issues.
No,
We have some gifts to give you, and we'll send them to you somehow.
sure.
Yes.
Yeah.
Does anyone have any questions? Okay. So thank you very much, sir. We'll get back to you with the gifts.
Yeah, great. I wish you people, a lot of fun doing math, and not only math, of course, STEM, but then you must understand that math is everywhere. So it's the backbone of everything. So enjoy. All right, and do great science. Yeah. Bye.
Thank you.
Yeah. Thank you. Yeah.
Thanks.